Okay, in this kind of opening problem, I just wanted to talk about some ways we could find the area in the first quadrant enclosed by this curve. And there we actually have a couple of options. The first option is if I solve this equation for y. So if I had, y equals, and of course I would subtract 2x from both sides and then divide everything by 3, so I would have 2 minus 2/3 x. Well, I could integrate that. And because I'm doing this with respect to x, the bounds would be 0 and 3. Okay, so then I would do the antiderivative. Evaluate at 3 and 0. I plug in 3, I would get 6 minus 3, which is 3. Plug in 0, I get 0. So the area is 3. The other way I could do this, I could solve for x, the original equation, and then I of course would have 6 minus 3y, and I would have divided everything by 2, so I would have 3 minus 3/2 y. Well, now if I integrate that, I've got dy, so y is the axis I'm interested in, so now I'm integrating from 0 to 2. So the antiderivative would be 3y minus 3/4 y squared. Evaluate at 2 and 0. If I plugged in 2, I would get 3. If I plugged in 0, I would get 0. So again, you can see the answer is obviously going to be the same. Now, I just wanted to quick remind you, when we first started doing area, we would begin with rectangles. I'm just going to draw a rectangle right there. Of course, we would estimate. And we always said, to find the area of the rectangle, area would be equal to, well, we needed a base. We would call it delta x. And we needed a height, and we got the height by actually evaluating the function. So the area was this. Now, as we began to add all those up, we would designate that with, the sum of all of the rectangles. And we transitioned this, and we proved it, into the integral of the function. We have dx. And the dx took the place of our delta x because, of course, we wanted smaller and smaller rectangles. So our goal was to make delta x approach 0, and when that happened, the number of rectangles we were using approached infinity. And again, then this transition occurred where we integrated the height dx. And I want you to keep that in mind because we're going to use that as we begin to find volumes. So if I revolve that shape from the opener around the x-axis, I want you to think about this. So if I took this thing and revolved it around, okay, so like that, what shape I would end up with? Well, I'd revolve it out from the screen like that. Of course, the back would something like this. It would look like a cone. Okay, now I'm going to erase this kind of back three-dimensional line for now just so it doesn't get in the way. And instead now of if I drew that rectangle in, if I took that rectangle and revolved that around, okay, if I revolve that around, and let me kind of erase it again just so it doesn't get so muddled, but I take this rectangle and I revolve it around. Okay, and it had a little width. Come around like that. It would look like that. So that rectangle, as it's spun around, begins to look like a cylinder. and the cylinder has a volume of a cylinder is pi r squared h. And again, I'm going to use the same idea as I did with the integral. So I begin by looking and saying, well, when it was a rectangle, we called this, delta x, and we got the height of the rectangle by using the function, but now that height would represent the radius. Okay? So let me replace that then. I'm going to transition here to have pi. Instead of r, I'm going to have the function. And instead of h, I'm going to have delta x. But again, as we transition this into an integral, because of course we want delta x to get smaller and smaller, therefore meaning we have an infinite number of cylinders, this is going to become an integral of pi r squared, and then what used to be the width of the rectangle is now the height, so dx. And this is really the key to finding the volume of revolution. It's always pi multiplied by r squared. Now for me, I always, of course, would pull that constant out front. So for this, my integral would be pi multiplied by the radius, which again is the function. So from the opener, that function was 2 minus 2/3 x squared dx. And we're going to integrate this from 0 to 3. Okay? So that would find the volume. Now, if you actually wanted to do that, by hand, you would. I would start by maybe rewriting the inside as 2 minus 2/3 x multiplied by 2 minus 2/3 x dx. There's your r squared. So we began then by multiplying, 2 times 2, 2 times negative 2/3, negative 2/3 times 2, and so on. And we end up then with an integral. Pi is still up front. We're still going from 0 to 3. We have 4 minus 8/3 x plus 4/9 x squared. So we do the antiderivative. Pi is still up front. We'd have 4x minus, we'd raise the power and divide, so it would become 8. I'm just going to leave it unreduced. 8/6 x squared plus, raise the power and divide, so it would be 4/27 x cubed. Evaluate at 3 and 0, and we'd plug those in, multiply it by pi. I'm kind of out of room, but that's it. That will give us the volume. So the real secret here, if I can go back for a second, is what used to be a rectangle. We would just add up all the rectangles, and then we said, well, we get the height with f of x, we get the width with dx or delta x. We transition that to an integral. Now we're taking those rectangles and revolving them so they appear to be little cylinders, okay, that can kind of be sliced out. Well, the volume of a cylinder is pi r squared h, which we said was pi multiplied by the radius we got with the function's values, and the height was just that delta x. We transition that to this, and this is the big formula to know. So in this one, find the volume of the function on the interval when it's revolved around the x-axis. So again, we take something here and we revolve it like that. Yeah, I kind of like to think about it. It's going to come around like that. It's almost going to look like a football, when we revolve the whole thing around. So this is your dx or delta x. Your radius we get with the function. Okay, so remember we have pi multiplied by r. So the radius, and then we've got the width, and we integrate it. And we're going to go from 0 to 1. And again, this you know, it really is every time just pi, the radius squared. We get the radius by using the function, and this represents the height of our cylinder. Okay, so again, I would pull that pi out front, go down here and do my work. If you're going to do it by hand, you know, don't be afraid of doing that. Just rewrite it. So then I multiply it out. I've got x squared minus 2x cubed plus x to the fourth dx. Okay. The antiderivative would be 1/3 x cubed minus 1/2 x squared plus 1/5 x to the fifth. And we evaluate that at 1 and 0. And we multiply it by pi. And when you plug in 1, you get 1/3 minus 1/2 plus 1/5. When you plug in 0, you get 0. 1/3 minus 1/2 plus 1/5 is 1/30. So my final answer comes out to be pi multiplied by 1/30, which of course is just pi over 30. Okay, so it's not that hard to do it by hand. You just got to take it step by step. The big thing to remember is it's always pi r squared.